So again, welcome to the second day of class. Today we're going to talk about mostly trig functions, specifically trigonometric functions of special angles. We call them special angles because they're angles that, well, they're special. And we kind of expect to be able to evaluate them relatively quickly. So if someone asks you in the future, what's sine of 30 degrees? What's cosine of 45 degrees? There's usually some expectation that we be able to answer that relatively easily. On the other hand, something like cosine of 2 degrees or sine of 47 degrees, that's something that nobody really knows off the top of their head, and we would all use a calculator for. So today we're going to talk about trig functions of special angles and then a couple other topics. So just as a reminder from last class, let me actually do one thing here. I feel like sorry, one sec. I want to modify one thing. A little better. Okay. Last class, we defined the 6 trig functions for a right triangle. If you're looking at an angle theta or whatever you want to call it, this longest side is always the hypotenuse. The other side next to it is the adjacent side. And then the third side that doesn't touch, that the angle, right, the side the angle doesn't touch at all, this side, that's the opposite side. And then we defined sine of theta to be the opposite divided by the hypotenuse, cosine of theta to be the adjacent divided by the hypotenuse, and tangent of theta to be the opposite over the adjacent. And then we have the 3 reciprocal or flip trig functions. Cosecant theta is the reciprocal of sine, its hypotenuse over opposite. Secant theta is the reciprocal of cosine, its hypotenuse over adjacent. And cotangent theta is the reciprocal of tangent theta, it's the adjacent over the opposite. So that's all stuff that we're going to fall back on all the time. When you think about the definition of the trig functions, these are things that you should kind of be like, okay, yeah, that's sine, that's cosine, etc. But let's go ahead and look at some very specific angles that we're going to evaluate all these trig functions at. Also, for those of you that are new today, I will be posting all of these notes on Canvas after class. So if there's anything you don't get down, don't sweat it. It'll be there relatively quickly after class. I will also, a little bit later after the video has compiled, post the video from class as well. So if you ever want to go back and look at something, it will be there on Canvas not too long after class is over. So let's talk about some special triangles. We're going to start with a square, a 1x1 square, and we're going to cut it in half on the diagonal. And a square, all the angles are 90 degrees. But if we cut this in half diagonally, this angle here is going to be how much? It's going to be 45 degrees. This angle up here is also going to be 45 degrees, but I'm going to write it in radians instead. So both those angles are 45 degrees, or both those angles are pi over 4 radians. Now what we're going to do is we're going to find the third side of the triangle. So we still have this side is 1 and this side is 1, but this side here, the hypotenuse is unknown. Let's call it h. So we're going to solve for h so we can then evaluate all the trig functions. Actually, there's one trig function, well, really 2 trig functions we could already evaluate. We could totally find tangent of 45 degrees. Tangent is opposite over adjacent. That would be 1 over 1, which is 1. But we need the hypotenuse to find the other 2 primary trig functions. Let's go ahead and do that. So Pythagorean theorem, it's going to be 1 squared plus 1 squared equals the hypotenuse squared. 1 plus 1 is 2. So 2 is the hypotenuse squared. So the hypotenuse is going to be the square root of 2. And yes, it's the positive square root of 2. We're not worrying about any negative side lengths here. So this here is the square root of 2. And now we can find sine and cosine and tangent and the other 3 reciprocal trig functions. So let's go ahead and do that. So sine of, I'm going to write pi over 4 because I will tell you, even though we will definitely use degrees and radians both, calculus works best in radians. And so you really want to get very comfortable using radians. So I'm going to try to more often than not default to using radians, although degrees certainly do get used as well. So sine of pi over 4 radians, well, we can look at these angles are the same, right? 45 degrees is pi over 4. So looking at this angle here, the opposite over the hypotenuse is 1 over the square root of 2. Now yesterday, I don't remember who asked, but somebody asked about rationalizing the denominator, and we should do that here. So let's go ahead and multiply both the top and the bottom by the square root of 2. 1 times the square root of 2 is the square root of 2. And any square root times itself is just the number you're square rooting. Right? The square root of 2 times the square root of 2 is the square root of 4, which is 2. But I kind of want to make that clear over here just for a second. Whenever you multiply a square root, so a square root of some stuff times the square root of the same stuff is just equal to the stuff. Always true. Well, it's always true if the stuff is positive. If your stuff is negative, it's a little dicier there. So true with a grain of salt. Let's find the rest of the trig functions. Cosine of pi over 4. So if we look at this angle, the adjacent side is 1, the hypotenuse is root 2. So it's also 1 over root 2, which we know if we rationalize is the same as the previous one. It's going to be root 2 over 2. When I think about the angle pi over 4 radians or 45 degrees, the first thing I really think of is that for that angle, sine and cosine have the same value. That's kind of like the number one fact I keep in my mind about 45 degrees. Sine of 45 degrees is root 2 over 2. Cosine of 45 degrees is also root 2 over 2. And then tangent of 45 degrees or pi over 4 radians is equal to 1 over 1, which is 1. Let's do the other 3. Hopefully I left myself enough room here. Cosecant of pi over 4. So I'm going to do this kind of the short way first. I'm going to think of cosecant as the reciprocal of sine. If I take the reciprocal of sine, well, if I look at the kind of original thing we got, which is 1 over root 2, the reciprocal of 1 over root 2 is just root 2 divided by 1, which is just the square root of 2. There's a lot of different ways to get there. We could have said cosecant is the hypotenuse over the opposite, which is also root 2 over 1. Or we could have even said cosecant is the reciprocal of sine. Now, what I really mean is people often do this. We could say cosecant of pi over 4 is the reciprocal of sine of pi over 4. This is going to be kind of a long way. Oh, no worries, Anthony. We're just talking about taking sine and cosine and all the trig functions of some special angles. Right now we're talking about 45 degrees or pi over 4 radians. That would be 1 over root 2 over 2. And then, as I imagine we've seen, when you divide by a fraction, you flip a multiplier. Some people say copy dot flip. You do 1 times 2 over root 2. 1 times anything is just itself. And 2 divided by the square root of 2 is just the square root of 2. I'm not saying you should do it that way. I'm just showing you some people think about things differently. Just like sine and cosine are the same for this angle, secant and cosecant should be the same as well. So cosecant of pi over 4 is root 2 over 1. Secant of pi over 4 is also root 2 over 1, which is just root 2. And finally, cotangent of pi over 4 is just 1. It's the reciprocal of tangent, which is 1 over 1, which is 1. So when I think about the angle pi over 4, I think about sine and cosine being the same. They're both root 2 over 2. So that's one of the special triangles. There's another special triangle. Also, if you have questions, I might not see because I can't see everyone at once the way I have things set up. So I could scroll through. So I won't see you if you actually raise your hand in real life. I might not see you, but if you click the little raise your hand thing or just say words or type in the chat, I will certainly address any questions you guys might have. Let's go on to the second special triangle. An equilateral triangle. So this one's actually a triangle to start with, but we're going to, with the square, we're going to cut it in half. So this equilateral triangle has side lengths all 2. And all the angles are 60 degrees, or pi over 3 radians, which is the same as 60 degrees. But then we're going to cut this triangle in half vertically, just like that, so that we still have a 60-degree angle here, which is also pi over 3 radians. But this angle up here that was 60 degrees over here is also going to get cut in half. And half of 60 degrees is 30 degrees. And half of pi over 3 radians is pi over 6 radians. And now let's look at the side lengths. This long side here didn't change, still 2. This bottom part got cut in half, so it's half of 2, which is 1. And this third side here, which we don't know, we're going to find. So let's call it x, and we're going to find x. Pythagorean theorem. So whenever you're missing the side in the right triangle, you can always use the Pythagorean theorem to find it. So we're going to have 1 squared plus x squared equal to 2 squared. It's also important to remember that whenever you're using the Pythagorean theorem, the hypotenuse side squared is always the side that's by itself. And then I'm going to solve for x. So x squared is going to equal 4 minus the 1, which is 3. So then x is going to be the square root of 3. So now we have the 3 sides of a right triangle, and we can find sine, cosine, tangent, etc., of whichever angle we want. So let's do 30 degrees first, or pi over 6 radians. So I'm going to find sine of pi over 6. Let's see. So there's pi over 6, and sine is the opposite over the hypotenuse. So that's going to be 1/2. Cosine of pi over 6 is going to be, so again, I'm looking at this angle up here. It's going to be the adjacent over the hypotenuse. So it's going to be the square root of 3 divided by 2. Tangent of pi over 6 is going to be the opposite over the adjacent. That's going to be 1 over root 3. Again, we should rationalize. So we're going to multiply by the square root of 3 over the square root of 3. And we'll end up getting the square root of 3 divided by 3. So this is why we do these 3 first, because then the other 3 are super fast. Just have to remember that cosecant is the reciprocal of sine and secant is the reciprocal of cosine. I feel like it's pretty easy to remember that cotangent is the reciprocal of tangent because like they have the same name in them. One way I remember which one goes with which, well, I'll say this afterwards actually. So let's do it first. So cosecant of pi over 6, it's just the flip of sine. So it's going to be 2 over 1, which is 2. Or you could look at the triangle and say it's the hypotenuse over the opposite. Secant of pi over 6 is going to be the hypotenuse over the adjacent, or just the flip of cosine. 2 over the square root of 3, which again, we should rationalize. So we're going to end up with 2 root 3 over 3. And then cotangent of pi over 6. So here's a point where we want to kind of be smart about our work. We could do the reciprocal of this, or the flip of this, and say it's 3 over root 3, but then we'd have to rationalize again. We could also say it's just the reciprocal of this, root 3 over 1, which is just root 3. And if you look at the triangle, that also works, right? You could say, oh, cotangent of pi over 6 is the adjacent over the opposite, which is root 3 over 1. So there are the 6 trig functions of pi over 6 radians, or 30 degrees. And again, I'll just point out, you're going to get asked a lot over your mathematical career. Oh, what is sine of pi over 6 or cosine of pi over 6? And something that you're going to hopefully do enough that eventually be like, oh yeah, I just know it. It's something you kind of memorize through repetition of doing. But it is something that's going to come up frequently enough that you want to have memorized it. So you're not always like, okay, what's sine of pi over 6? Let me get my calculator or whatever. There was something else I wanted to mention here, is that when I think about the reciprocal pairs, here's how I kind of remember which one goes with which. Tangent and cotangent obviously go together. They have like the same name. And then which one goes with sine and which one goes with cosine? I remember that each kind of pair of reciprocals, one of them starts with a co. So sine and cosecant go together as reciprocals, and cosine and secant go together. So each pair, there's a non-co and a co. There's a non-co and a co. There's a non-co and a co. It's not like the most intuitive thing ever, but it's something I've definitely noticed over the years. So I just thought I would mention it. So let's talk about the other angle. In fact, I think I'm going to give you guys a chance. I want you all to find sine of pi over 3, cosine of pi over 3, and tangent of pi over 3. The triangle is already there. There's the angle we're looking at. I think you can do it. I'm going to give you, I don't have a good watch detail. I'll just give you a few, I'll give you a little bit. This thing. All right, I'm going to keep going. So I was thinking, it's unfortunate I can't walk around and see what you guys are doing, because I would love to actually look at your work and be like, oh yeah, you're doing all right, or here's how you do it. But it's not the reality we live in. So here's what we've got. So you're going to see a lot of the same values here, because these angles are what we call complementary, and that happens a lot with complementary angles. So sine of pi over 3 is going to be the opposite of the hypotenuse, which is √3/2, which is the same as cosine of pi over 6. And cosine of pi over 3 is going to be adjacent over hypotenuse, which is 1/2, which is the same as sine of pi over 6. And tangent to pi over 3 is going to be √3/1, which is just √3. And then the other three reciprocal functions, cosecant of pi over 3 is going to be 2/√3. And we already know how that rationalizes. 2/√3 is the same as 2√3/3. Secant of pi over 3 is going to be 2/1, which is just 2. And cotangent of pi over 3 is going to be 1/√3, which rationalizes to √3/3. So all these values are the same as all those values. They're just associated with different trig functions. And that's always true for the complementary angles in a right triangle. Right? If you're taking trig functions of this angle or trig functions of this angle, you're still using the same side of the triangle. They just have different roles. So here, right, sine of 60 is √3/2. Here, cosine of 30 degrees is √3/2. Kind of interesting. Let's go ahead and talk about a few other angles. Yeah. So these are the special angles that are between 0 and 90 degrees, or 0 radians and pi over 2 radians. But we often want to be able to find sine, cosine, tangent, etc., of angles that are larger than 90 degrees, larger than pi over 2 radians. And there's a couple ways of doing that. One way of doing it, which we'll talk about right now, involves just kind of thinking about if things are positive or negative. So let's go ahead and take a look at this next example. Let's say we want to find, and let's stick, we'll do trig functions of theta equal to 3 pi over 4 radians, which is the same as 135 degrees. And what we're going to do is we're going to draw it in the coordinate system. So obviously, or maybe not obviously, but somewhat, it seems obvious to me. You can't draw a right triangle that has a 135-degree angle. Right? The angles of a triangle have to add up to 180 degrees. And if one of them is 135, you can't have a 90-degree angle also. So here's what we're going to do. We're going to draw this 135-degree angle with this 3 pi over 4 radian angle in the usual way, where we start with 0 being the positive x-axis. So over here, this is theta equals 0 or theta equals 0 degrees, right? Depending if you're using radians or degrees. And then we're just going to measure 135 degrees counterclockwise. So we're going to go like that. That's a 135-degree angle approximately. Then what we're going to do is we're going to drop a perpendicular to the x-axis. Always, always, always to the x-axis. And then we're going to label what we're going to call eventually the reference angle. So this angle right here, that's measured to the x-axis, is a nice angle. It's not 3 pi over 4, it's pi over 4. Or 45 degrees. And one way you can think about it is, we talked about yesterday how a semicircle has an angle of pi radians. Well, that's all we're really doing here is we're seeing, oh yeah, look, from here all the way to here, that's pi radians. So if this angle is 3 pi over 4, then we need another 1 pi over 4 to get a full pi. So that's how we know that this angle here is pi over 4. So now we know what the triangle for pi over 4 looks like, right? We just looked at it. The sides are 1, 1, and the hypotenuse is root 2. There's just going to be one small difference. We're going to say that this side is -1 because we're on the negative x side now. This side up here is still +1, and the hypotenuse is always going to be positive. Exactly, Nayeli. This is a reference angle for sure. So what we're going to do is, what I should say is, we're doing it this way at first, but you can totally kind of bypass this and just be like, I know how reference angles work. But the idea here is that we're going to say, we already know essentially everything. Sine of 3 pi over 4 is just going to be 1 over root 2, right? It's going to be the opposite over the hypotenuse, which is going to rationalize to root 2 over 2. But cosine of 3 pi over 4, instead of being positive root 2 over 2, it's going to be negative root 2 over 2, because it's going to be -1 divided by root 2, which is negative root 2 over 2. And tangent of 3 pi over 4 is going to be the opposite over the adjacent, which is going to be 1 over -1, which is -1. And then we could also do the other 3. It seems not super necessary, but yeah, in fact, let's not do the other 3. Let's just stick with the 3 primary ones, and we'll assume everyone is comfortable with flipping all those numbers over to get the other 3.
Wait, I'm kind of confused. Like,
go ahead.
how would that be like the numbers for 3 pi over 4 and not pi over 4?
So sorry, say that one more time. I didn't quite hear you.
Like, I'm confused at why it would be the values for like sine 3 pi over 4 and not the values for like sine pi over 4.
Well, so actually for sine, they are the same. Sine of 3 pi over 4 and sine of 1 pi over 4 are both equal to root 2 over 2. But for cosine, they're a little bit different. Cosine of pi over 4 is positive root 2 over 2. But cosine of 3 pi over 4, since the angle 3 pi over 4 gets us into this area where kind of the adjacent side is going to be negative, then we end up getting a negative value for cosine. So we end up getting -1 over root 2, right? The adjacent over the hypotenuse. And then that rationalizes as negative root 2 over 2. So it really just depends on, what quadrant your angle terminates in. That's going to determine the sign, the SIGN sign of your trig functions, sine, cosine, etc. So let's look at another example. Let's do that one. And then we'll talk about kind of, so I'm kind of doing this the long-ish way at first, and then we will talk about kind of the faster way to do it. But the point I want to make is we're still using the values we got from our special triangles, right? We're using the angles pi over 4, and we're going to use pi over 6 and pi over 3. And then we're just going to adjust to see if it's positive or negative. That's really kind of the whole deal for finding the trig functions of all of the special angles. So let's look at the special angle. Let's say we want to find the trig functions of 4 pi over 3. So let's draw it. 4 pi over 3 is actually a little more than pi, right? 4 pi over 3 is 3 pi over 3 plus pi over 3. The 3 pi over 3 is just pi. So that's pi plus pi over 3. So when I draw this, again, starting at the positive x-axis, I'm going to go a full semicircle. There's pi. Then I'm going to go another pi over 3, which I didn't draw it very well. That looks more like pi over 4. I'm not going to lie. I'm going to draw it again. Sorry. Let's try one more time. Really, I should just draw where I know I'm going to end up. There. So there's a pi and a pi over 3. So we're doing trig functions of so there's an angle 4 pi over 3. And notably, well, first of all, let's talk about the reference angle. Drop my perpendicular to the x-axis. And this angle here, that's a pi over 3. Because, right, it's pi plus pi over 3 to get you to 4 pi over 3. So we're using the special triangle with pi over 3 is the angle, and the sides were 1 and the square root of 3 and 2. The only difference here is that now, instead of being a positive 1, it's a negative 1. Instead of being a positive root 3, it's a negative root 3, because we've gone left and down instead of right and up. And the hypotenuse is always positive. Essentially, the hypotenuse is kind of considered to be the radial distance from the origin. So it's always a positive number. Whereas these have kind of a direction left or right or up and down. Left is negative, right is positive, up is positive, down is negative. So here, we can find sine of pi over 3. It's just going to be opposite of hypotenuse, which is negative root 3 over 2. It's still essentially the same value. Oh, sorry, I wrote the wrong thing. Sine of 4 pi over 3 is negative root 3 over 2. What I'm actually thinking of really is that sine of 4 pi over 3 is the negative of sine of pi over 3. I know sine of pi over 3 is root 3 over 2. I know sine of 4 pi over 3 is going to end up being negative. So it has to be negative root 3 over 2. Cosine of 4 pi over 3 is going to be the adjacent side over the hypotenuse, which is going to be a negative 1 over 2. And tangent of 4 pi over 3 is going to be the opposite over the adjacent, which is going to be negative root 3 over -1, which ends up being positive √3. And let's go ahead and talk about the other ones as well, because what I want to say about the other three reciprocal trig functions is they all have the same positive or negativeness as their original function. So cosecant, and I didn't leave enough room to write them side by side, sorry. So cosecant of 4π/3 has to be negative because sine is negative. So it's going to be -2 over √3, which rationalizes as -2 √3 over 3. And secant of 4π/3 has to be negative because cosine is negative. It'll be -2 over 1. And cotangent of 4π/3 has to be positive because tangent's positive. It's going to be 1 over √3, which is √3 divided by 3. So there's a couple more examples in the previous notes that I'm going to skip over because what I really want to say is it all depends on what quadrant the angle lives in. Oh yeah, we got, let me do, I said I was going to skip over. Yeah, let's go ahead and talk about the quadrants. So there's a lot of things you could write, but there's kind of an easy way to write it all down. So this is quadrant 1 over here, quadrant 2, quadrant 3, and quadrant 4. And in quadrant 1, everything is positive. So all trig functions are positive. And we've already seen that, right? We saw, right? We looked at angles that were between, right? So this is from theta equals 0 to theta equals π/2. If your angle is between 0 and π/2, did you draw? Oh, sorry, I didn't see that question there. Oh, that's a fair question. So let me back up just one second, sorry. So the reason I drew this triangle without the negatives is because it was kind of the original special triangle in the original orientation where the angle is π/3. But then when I put it over here, since we're going left and down, we're kind of thinking about the orientation. That's why we're drawing it that way with the negatives, because we end up with we're going left and down. But and what I'm going to say now is that's a fine way to think about it. But really what we're going to do is we're going to try and make it easier, which is always my preference. If there's an easier, more succinct way of doing it, that's usually what I want to do and want to show you. So in the first quadrant, all trig functions are positive because you could always draw a right triangle where all the side lengths are positive. And we could write a bunch of stuff. We could say that sine is positive and cosine is positive and tangent is positive. And you could also write the other three, but what I'd really like to impress upon you is just that whatever is true for the original function is also true for the reciprocal function as far as if it's positive or negative. So if you know that sine is positive, you automatically know cosecant is positive. Same for cosine and secant, same for tangent and cotangent. Or what I should really say is flipping something never changes its positive or negativeness. Right? If you take the reciprocal of -2, it's 1 over -2, which is still negative. Okay, in quadrant 2, sine is positive. So sine is greater than 0. And the other two primary trig functions, cosine and tangent, are less than 0. Now, there's a reason for this that we haven't quite gotten to yet. It has to do with the unit circle and how, and kind of the next way we define the trig functions. But what I kind of want to leave that for the next class and just kind of focus on this. So yes, there are questions. You might ask, why do we know cosine is negative and tangent is negative? Well, it has to do with like I was trying to avoid answering the question then, right? It has to do with how we drew the triangle, right? If the triangle is on the left, then the adjacent side is going to be negative. But if it's up here, right? So if we're drawing our triangle like this, this side's negative and this side's positive, and this side's positive. So that's why sine's positive because it's opposite over hypotenuse. Cosine's negative because it's adjacent over hypotenuse, and tangent's negative because it's opposite over adjacent. And then if you're down here in quadrant 3, now the adjacent and the opposite are negative. So sine is going to be negative because it's opposite over hypotenuse, which is negative or positive. Cosine is going to be negative because it's adjacent over hypotenuse. But tangent is going to be positive. So in quadrant 3, we say that tangent is positive. And finally, in quadrant 4, well, we've done sine is positive, then tangent is positive. The last one to be positive is cosine. So in quadrant 4, cosine is positive. So we have sine is negative, cosine is positive, and tangent is negative. For the same sort of reasons as before, right? If we draw the little kind of triangle, well, we can see that this side's positive, this side's negative, and this side's positive. So cosine is the adjacent over hypotenuse, that's a positive or positive. Sine is the opposite over hypotenuse, it's a negative or positive. So it's a lot of explanation, I know, to get to a mnemonic device I imagine some of you have heard of. All students take calculus. That tells you which of the primary trig functions is positive in the corresponding quadrants. So in quadrants 1, 2, 3, and 4, we have all trig functions are positive, sine is positive, tangent is positive, cosine is positive. So what does that mean for us? Well, it means we can use this knowledge to kind of find what sine or cosine of an angle is without having to, sorry. One moment, I have to dance around, turn the lights back on. I don't move enough when I'm just standing here. So what I'm saying is we could totally use this to find out what's happening with, say, the trig functions of, let's go, what do they do? Of theta equal to 11 pi over 6. Okay, so 11 pi over 6 is really close to 2 pi. We're just short by 1 pi over 6, right? 11 pi over 6 plus pi over 6 would be 12 pi over 6, which is 2 pi. So we're almost 1 full revolution, but not quite. We're kind of like that. There's 11 pi over 6. But what's really important is the leftover bit measured to the x-axis always is pi over 6. And we know how to evaluate sine, cosine, and tangent of pi over 6. Here's our special triangle for pi over 6, where the opposite side is 1, the adjacent side is √3, and the hypotenuse is 2. I should point out, it's the same as this triangle, just reoriented, right? It's that triangle, but now we're looking at this angle instead. And I know that sine of pi over 6 is equal to 1/2. So what that tells me is that sine of 11 pi over 6, let's see, I'm in quadrant 4 where cosine is positive. That means sine has to be negative. So sine is going to be negative 1/2. I also know that cosine of pi over 6 is positive √3 over 2. So cosine of 11 pi over 6, well, in quadrant 4, cosine is positive. So it's still going to be positive √3 over 2. And I'm just writing, I would normally not write positive, but I'm just writing positive to emphasize it. And then tangent of pi over 6 is normally 1 over root 3, which is root 3 over 3. Tangent of 11 pi over 6 is going to be negative root 3 over 3. Because again, we're in the quadrant where cosine is positive and the other two is negative. And then after we do the primary 3, we can very easily do the reciprocal 3. Cosecant of 11 pi over 6 is just the reciprocal of negative 1/2. So it's going to be negative 2. Secant of 11 pi over 6 is going to be the reciprocal of that, which is 2 over root 3, which rationalizes to 2 root 3 over 3. And cotangent of 11 pi over 6 is the reciprocal of this. So it's going to be negative, right? Because we don't change signs when we reciprocate. And the reciprocal of 1 over root 3 is root 3 over 1, which is just negative root 3. So we're definitely going to do more of that a little bit later. I always, when I teach this part, tend to get ahead of myself. So I'm like, oh yeah, we should go here. But then I'm like, oh wait, there's other stuff. So the idea is just that we can definitely find sine, cosine, tangent, all the trig functions of angles that are larger than 90 degrees by thinking about what quadrant they're in. So let's look at this last bit here. So there is kind of one other thing we like to do with this information. So let's say we knew some stuff about an angle. We actually didn't know what the angle was. Let's say we know that cosine of some unknown angle is equal to negative 3/5. And we also know the tangent of that angle is positive. Find the other trig functions of this angle. We're not going to ever find the angle itself, but we can definitely find sine and tangent and cosecant and secant and cotangent. And so the whole idea here is to draw a picture. There's actually 2 pictures I'm going to draw. First picture is going to be just of a triangle. And personally, even though I said that cosine is negative 3/5, I'm going to kind of ignore the negative. So I'm going to say, all right, here's my angle. I know cosine is the adjacent side over the hypotenuse side. You can put a negative in there if you want. It doesn't really matter. And now I need to find this other side. Pythagorean theorem to the rescue. And it doesn't really matter because we're going to squaring it. If it's negative or positive squared, it's going to still come out to be positive 9. So negative 3 squared plus x squared equals 5 squared. X squared equals 25 minus 9. X squared equals 16. X equals 4. So now we can find sine and cosine and everything of this angle. We can say, well, so I'm going to write down some stuff. It's not going to be exactly right yet, but I'm going to fix it. So I know that sine of theta is probably 4 over 5. But it might be negative. I already know cosine, but I'm going to write it down anyway. Cosine of theta is negative 3 over 5. And tangent of theta, well, actually, I know tangent has to be positive because they told me it was positive. Right there. They said, oh yeah, tangent's positive. So tangent of theta has to be positive 4 over 3, opposite over adjacent. And then cosecant of theta is the reciprocal. Secant of theta is the reciprocal. Cotangent of theta is the reciprocal. Now, this doesn't really look quite right. And the reason it doesn't look right to me is there weren't any quadrants where cosine was positive and where cosine was negative and everything else was positive. If something's negative, you have to kind of have the 2 of them are negative. So what I'm really trying to say in the longest way possible is we should figure out what quadrant the angle is in. And it's actually pretty straightforward. If you know that cosine is negative, Well, I know if cosine's negative, I can't be here and I can't be here. And I know if tangent's positive, I have to be here. So we're in quadrant 3, where tangent is positive and sine and cosine are both negative. So that means this sine should actually be negative 4/5, and this cosecant should actually be negative 5/4. Cosine is right, being negative, as is secant, and tangent is right, being positive, as is cotangent. So when I'm trying to tackle a problem like this, I try to think about what quadrant I'm in so that I know whether things are positive or negative. And then I try to think about what the values are based on the usual trig function kind of stuff. Let's do one more example, which is probably all we have time for. Water bottle really makes a lovely noise. Let's say we've got a similar situation. Let's use a different Greek letter just for the fun of it. Again, no meaning behind it, just good to practicing different things. So let's say we had sine of alpha equal to negative 7/8. And we also know that tangent of theta is negative. Let's find all the trig functions. Sorry, so I'm so used to using theta, I automatically use theta there. I should have said tangent of alpha. Apologies. It's very, very ingrained to just use theta as the angle because it's just so common. So before we even start talking about the values, let's talk about what quadrant we're in. We're not in quadrant 1 because something's negative. We're not in quadrant 2 because sine is negative. We're not in quadrant 3 because tangent's negative. We have to be in quadrant 4. So in quadrant 4, cosine will be positive and sine and tangent will both be negative. So we can even start writing it out. We know that sine of alpha, we already know it's negative 7/8. Whatever cosine ends up being will have to be positive. And whatever tangent ends up being will have to be negative. So now let's draw our triangle. And when I draw the triangle, I'm really going to ignore the negative signs. Here's my not very good triangle. There's my angle alpha. And I know that sine is the opposite over the hypotenuse. So since sine is 7/8, ignoring the negative, I'm going to say the opposite side 7 and the hypotenuse side's 8. And then we're going to find the adjacent side. Pythagorean theorem again, x squared plus 7 squared equals 8 squared. So x, whoops, not 8 to the 6th, 8 squared. So x squared is going to equal 8 squared, which is 64, minus 7 squared, which is 49. 64 minus 49 is 15. So x is going to be the square root of 15. And there's nothing else we can really do with that. We just have to leave it as the square root of 15. So then cosine of alpha is going to be adjacent over hypotenuse, which is the square root of 15 over 8. Tangent of alpha is going to be negative 7 over the square root of 15, which we then rationalize to get negative 7 root 15 over 15. And then we do the flips. Cosecant of alpha should be negative 8 over 7. Secant of alpha is positive 8 over root 15, which rationalizes as 8 times root 15 over 15. And cotangent of alpha should be negative root 15 over 7. So that's how we can use the quadrants along with our other knowledge to kind of tell us, oh, if we know the angle is in quadrant 4, we know cosine will be positive and the other two will be negative. If we know the angle is in quadrant 3, we know tangent's positive, the other two are negative. If we know the quadrants and the angles in quadrant 2, we know sine's positive, we know the other two are negative. And that's really useful when we start talking more about saying, okay, this angle has a certain reference angle, so we know what all the values are of the trig functions, and which we kind of already did an example of earlier. And then if we know what quadrant the angle is in, we can definitely determine all of the values for all of the trig functions without having to do too much work. That's what we're going to talk about tomorrow. That's all I have to say for today. I should also, before I go, two things, maybe only two things. The next homework assignment is due not tomorrow, but Thursday. And it will cover stuff from class today and from class tomorrow, but you should definitely get started on it. And I changed my office hours for Mondays and Wednesdays. They were from 9, sorry, not for Monday, for Tuesdays and Thursdays. They were from 9 to 11, but I know you guys kind of have, most of you have math D. I think all of you have math D from like 9:30 to 10:45. So that didn't really work for a lot of you. So I changed my Tuesday, Thursday office hours to be 10 to 12. So if you guys are looking for someone to come talk to between 10:45 and 12, I will be available. And I think that's all I've got. I'll hang out here for 5 to 10 minutes if any of you want to stick around, ask questions about anything class related, homework related, whatever. But if you don't have anything, you're certainly free to go. Nice meeting those of you that are new, and I'll see you all tomorrow.
So like in the previous problem, you had some numbers that were negative, but some numbers were positive, but then you changed them to negative because of the quadrants. Do we just have to like make sure we're following the quadrants as well?
Well, so that's a good question, Kristen. There's kind of two different ways you can do it. So normally for this one, what I would have really done is I would have ignored this negative completely. I would have said, I don't care about that. I'm just going to say it's 3. That would totally work fine. Or what you could do, and then, sorry, and so we ignore that. We just say this side's 3, this side's 5, and then find the 4 here. And then after we've done that, we can say sine is 4/5, but then we know we're in quadrant 3, so we know it has to be negative. So I suppose the answer to your question is mostly yes. I kind of ignore the negatives and then just look at what quadrant I'm in to figure out if it's positive or negative. There are kind of other ways of doing it. Like you could totally be like, well, you could have used this information to say, well, if cosine's negative and tangent's positive, I can draw my triangle like down here and say that this side's like -3 and this side's +5 and this side ends up being -4. But I feel like that's more work than I want you to have to do. Like doing it this way, I think requires us to have to unnecessarily work harder. Not that it's not fine to work harder, but doing it this other way, I think it's a better system. This way is going to work kind of all the time, regardless of whether we're doing this kind of thing or if we're trying to find like tangent of 5π/6, or it's an angle we know how to find tangent of in a different quadrant. Hopefully that kind of answers your question.
Yeah, it does. Thank you.
So what I would say, just to sum up there, is that I would kind of, whenever I'm doing this kind of problem, just like I did kind of in the next one, right? I totally ignored the negative. I just drew a triangle that had 7 and 8 as the opposite and hypotenuse, found the other side, found the values, and then fixed whether it was positive or negative based on being in quadrant 4.